put a question like this in our preview activities, and it's just to remind you that we have two basic operations that we can use whenever we're comparing two quantities. One is through subtraction. You compare two quantities through subtraction, and the other is through division. So today we're going to be looking at various problems where we're asking questions like, how many more times is one earthquake more intense than another, or how many more times is the noise made by a rock band more intense than, say, the normal conversation level. We might be comparing other things that involve logarithmic scales. And when we ask questions about how many more times, you should think of division, comparison through division. So I think probably most of you here, and let me know if I'm wrong, have 2 times. Is that true?
Yes.
Okay. And you can also remember, flip that ratio around when you ask, if I had asked about the relationship, say with, you can say 2 to 1 or 1 to 2, okay, depending on how you're looking at the question. So when it says how many times as much money does the engineer make compared with the social science, the engineer's salary is the numerator and the social science salary is the denominator. All right, so let's take a look at some earthquake numbers. Give me a sense of what you have for bad earthquakes and no big deal earthquakes. Well, just give me an example for bad earthquakes, what you might. Huh? 5? Anything else? 7, okay. 7 point, goes up to 10. How about this one? No big deal earthquakes. 1.5, okay. 4, okay. I'm trying to remember the one we had in Franklin County. So, was it? Yeah. It didn't?
No, my wife had to evacuate.
So this is just in the past 30 days right here. And you can actually find sites where they're recording earthquakes all the time. I mean, low-level earthquakes are happening all the time around the world. So the most recent one that we have recorded here is the Northeast Pacific rise. Was April 29th, was 6.6. So if you look down this this list here, you probably read about the earthquake in Ecuador. That was a pretty serious earthquake in Ecuador, and that was 7.8. And over here in this column, they have earthquakes, again, within the past day, earthquakes at a 2.5 or more. So they're using 2.5 as some kind of cutoff point. And so it must be that more than 2.5, it's worth noting. And you can see the Fiji Islands, today's the 13th, so this just occurred. And then this is kind of a nice site because it says today in earthquake history. So they mentioned back in 1995, there was an earthquake magnitude of 6.6 in Greece. So this magnitude, these numbers that you're used to seeing, is from a scale called the Richter scale. And the Richter scale involves, I'm trying to find my little, the Richter scale is a logarithmic scale, and it measures the magnitude of an earthquake. And this is the formula that defines or models the magnitude, M, of an earthquake, which is what you just saw beside that earthquake from Greece, M 6.6. And it's the log of I, where I is the intensity of the earthquake, divided by, and this is why I was having you do that little question at the beginning, S, where S is the intensity of what we call a standard earthquake, which is the smallest earth movement. So this is just a constant. So every single formula that we use to develop the magnitude of an earthquake with the Richter scale, this number is the same. It's constant for every single calculation. So that's kind of nice because you'll see that it divides out when we do our calculations. So one of the most famous earthquakes in the United States happened a while ago, more than 100 years, but it's worth noting. 1906, the earthquake in San Francisco had a magnitude of 8.3. It's really interesting to try to look at what we think is the earthquake that had the highest magnitude. That seems to be a little bit up for debate. But anyway, 8.3 is pretty serious. And if you go online and you look at any kind of information about the earthquake that hit San Francisco in 1906, it totally devastated, flattened the city, burnt it to the ground. At the same time as the waves from the epicenter spread west to Japan, the magnitude measured in Japan was 4.9, caused significantly less damage. So one of the questions that we always want to think about and ask and see, it gives you a sense of how logarithmic scales work, is to say how many more times intense was a San Francisco earthquake if we compare it to the Japanese earthquake. So what we're really doing, just like you did with the salaries, is we're asking how many more times is the San Francisco earthquake more intense than the Japanese earthquake. That's really what we're doing, that division problem. So let's solve for the intensity of each earthquake. The intensity is this value right here. So in order to solve for I, we're going to have to get rid of that log somewhere along the way. So let's take each city, well, the city of San Francisco and the country of Japan, one at a time. So the San Francisco earthquake, so the magnitude is equal to the log of the intensity of the earthquake divided by this standard earthquake, which again is just a constant. So I'm just going to make that green just so we know that that's a constant number. We don't have to search around our problem for trying to find it, right? I is what we're solving for. We're solving for I. So our only hopes of doing this equation is to get the information for the magnitude of the earthquake, and that's given to us in the very first sentence. It says the magnitude of the earthquake in San Francisco is 8.3. So I'm going to replace M with 8.3, and I'm going to solve this log problem. S somewhere, right? But you're going to see we don't really need the value of S. All right. So to solve any equation in mathematics that you're going to be dealing with, we need to do the inverse operation. This is a log, a common log. Its inverse is 10 to the power. It's an exponential equation, 10 to some power. So what's really nice, log equations are so easy to solve because you can convert every single log equation to its corresponding exponential equation. So we know that a log base 10 can be rewritten as 10 to some power. What power? Well, we know that every single log is an exponent. So the output of a log is the input of our exponential equation. So 10 to the 8.3 is going to equal I divided by S. So I just convert that log equation to its equivalent exponential equation. And now I multiply both sides by S to solve for I. In fact, on I, I'm going to put a little thing SF, just so I know that that's the intensity for San Francisco. So I multiply both sides by S, and I get 10 to the 8.3 times S is equal to the intensity of the San Francisco earthquake. Okay. So now I have my numerator. I can fill in my numerator right here. The intensity of my San Francisco earthquake is going to be 10 to the 8.3 times this constant S. So once I figure out the intensity of my Japanese earthquake, I just divide the two quantities. The S's won't matter because they're going to be the same in each. It will reduce to the factor of 1, right? So let's take a look at the Japanese earthquake and measure its intensity. So we know the magnitude of the Japanese earthquake was 4.9. 4.9 is going to equal the log of the intensity of the Japanese earthquake divided by, that's a J, divided by this constant S, which will make green. So I think we can skip the mathematics because I think we can look at the process we used in the San Francisco earthquake and wager a guess for I sub j. So see if at your seats you can wager a guess with either individually or with your table mates for what I sub j is. And if not, I can go through it. So try it on your own and then we'll talk about it. All 5 flags are up. Who's going to take the risk and tell me what they wrote for the intensity of the Japanese? Julia? Right, times S. Okay, so now we're going to put that right up here in this division problem, just like we did for the intensity of the San Francisco earthquake. So we have 10 to the 4.9 times S. So now we do this division, and if you notice, S over S is just a nice 1. And so our answer is 10 to the 8.3 divided by 10 to the 4.9. And how do I do that division problem if I don't have a calculator? Yeah, finally, you can see an application of why you need exponent properties when you're doing division with the same base, right? You subtract the exponents. You keep the base the same, and you subtract your 2 exponents. So these are the 2 magnitudes that you're subtracting, and you see 10 to the 3.4. Say 8.3, 4.9, not too much of a big difference, but remember you're raising 10 to that power. So now's the time you want to pull out your calculator and get a sense, an approximation of how much more intense that San Francisco earthquake was that totally devastated the entire city of San Francisco. So let's see, 10 raised to the 3.4 is 2,511.886. So approximately 2,500 times more intense. Okay, so based on the question asks how many more times more intense was San Francisco compared to the Japanese. So you're comparing it, your base is the Japanese earthquake, and you're trying to find out about the San Francisco. Okay, if it said Japanese compared to San Francisco, it would be the inverse, the reciprocal. Okay, it's just the way the language of how the question is set up. All right, so let's just take a little snapshot of that so you can have it for your notes. All right, there we go. All right. So what's important here is that it's how this relationship, this log scale, this is a common log. So every power that you increase 10 to the first, 10 to the second, 10 to the third, you're increasing by a factor of 10. Every time you raise that exponent by 1, when 10 is your base, you're adding another factor of 10. So with the Richter scale, if an earthquake's magnitude increases by 1, then its intensity increases by 10 and vice versa. So if I told you one earthquake was 1,000 times more intense than another, you would say, let's see, 1,000's 10 to the third. So their magnitudes are going to differ by 3 because it's 10 to the third. So this is just a nice little kind of general fact of knowledge to have when you're looking. You'll be seeing earthquakes for the rest of your life being reported in papers. You'll have a sense of their intensities, especially if you're comparing, say, earthquakes from one place to the other, or just with the aftershocks, which sometimes are more devastating than the earthquake themselves. So what would be a really quick way, now that we've seen this example, what could you do really quickly, like if you had a little piece of paper and a calculator to compare to the magnitudes of 2 earthquakes? You're not probably going to ever remember going through all this, but what could you do, Jasper? Yeah, and then what? Right. So all you have to do is always going to be base 10 because the Richter scale is the common log, so it's always going to be base 10. And here you have the magnitude of, say, earthquake 1, subtract the magnitude of earthquake 2. That will always work. So if we just went back here to what we just found on Google a minute ago, and we just wanted to compare, say, the earthquake that happened in Ecuador, 7.8, and we wanted to compare that, say, with the earthquake that happened today in Nevada, 2.6, let's see what the intensity ratio is. So 7.8 and 2.6. So we have 10 to the 7.8. So this is Ecuador, minus 2.6. This is Nevada. So that's 10 to the what? 5.2. So 10 to the fifth, you know, is 100,000, right? So this is a major difference here in terms of intensity. So let's take a look. 10 to the 5.2 is 158,500 times more intense. I'm glad I'm living in, I'm glad I would be in Nevada and not Ecuador. Okay. A couple of years ago when I was doing this demo was when the nuclear power plant in Japan had the the tsunami wave and the earthquake, everything happening there. That was unbelievable. So I don't recall what the magnitude was, but it was pretty high. All right, so basically that's the demo for today. You're going to have a lot of time today, so please try to stay focused. I know it's hard not to carry on with, you know, what are you doing for the weekend and what are you doing when school's out and my job is this and I'm getting married or whatever's happening. I'm having a baby, you know. We have quite a few things going on in this class. So you're going to get a lot out of today's demonstrations, the activities, excuse me, because we're looking at pH levels, we're looking at decibel levels, noise levels. So if you ever wonder why certain things hurt your ears when you hear loud noises, I would be very aware of how high you turn up your little earbuds. I have a real worry, you know, what do I worry about? I worry that this generation is going to be deaf by the time they're 40. But but the other thing I just wanted to show you, for those of you who may not be aware of pH scales, we say that pure water has a neutral pH at 7. Most of the water you find on planet Earth now is acidic. Maybe you've heard of acid rain, okay? And anything below 7, 1 to 7 has a pH that's between 1 and 7 is acidic. So some of those things would be like hydrochloric acid, lemons, vinegar, tomatoes, bananas, potatoes. And then anything to the right is called alkaline, or the more common word is basic. So that would be things like eggs and baking soda and I can't see what that is. Calamine lotion, maybe? I don't know what that is. Ammonia, bleach, and oven cleaner. And this last thing, I can't read either. What do you think that is? Anyway, I like this. I'm going to try to find the one that I had originally, which shows you the acid rain and fish dying and what the concentration of the acidic pH level is for the fish to die. And the reason I'm interested in that is that when I was in grad